Hi, I'm Gene Benson, and I would like to welcome you to our Pilot Talk series sponsored by Avemco Insurance. This presentation, along with all the presentations in the series, qualifies current and new Avemco customers for a discount on their insurance premium. Welcome to our Pilot Talk series of webinars. Today's event is titled Aircraft Engine Longevity and Reliability. I'm Gene Benson. I'll be your host once again today. In case you didn't know, Avemco is a sponsor of the FAST team, and they pay for the wings that we receive when we complete a phase of wings. At the end of this presentation, I'll tell you how you might be eligible for a discount on your aircraft insurance for attending this webinar and other events as well, so stay tuned. Start with just a bit of housekeeping. We usually begin our live seminars with telling you where the bathrooms are and the escape exits, but we'll leave that up to you to figure that out today. Our emergency would be some sort of a system crash. Unlikely, but if it should happen, we will post a revised time to do this on vectorsforsafety.com, and we will also let everyone know who was registered via email. All right, also on the controls with me is my friend and colleague, Elaine Lisser. Elaine will monitor the questions, so just type any questions you have into the Q&A box, and we'll do our best to address them. We'll stop a couple times during the presentation probably, but then we have allowed some time at the end to take care of that. Those of you who attended the Better Decision Making webinar, you'll remember Lane for sharing his engine failure story with us. If you missed that event, there is a recording available on my YouTube channel, and there is a link to the previous webinar recordings, all of them, on vectorsforsafety.com in the Pilot Talk section. Now to introduce our guest presenter for today, Shawn Benson is a graduate of Embry-Riddle Aeronautical University with a BS degree in Aviation Maintenance Management. He holds FAA certifications including A&P, IA, and Private Pilot. He's also a FAST team representative. He has more than 25 years experience in the aviation industry, including both airline and general aviation. Yep, we're related, if you couldn't tell. Shawn's my son. He was slated to do this presentation at AirVenture, but with that being canceled this year, he's doing it as part of our Avemco Pilot Talk series. His presentation last week on engine monitoring and reliability received lots of positive comments, so the pressure is on him to outdo himself today. And we want to also thank Aircraft Specialties of Tulsa, Oklahoma for the use of their slides in this presentation. Aircraft Specialty Services, they've been in business for 35 years, more than that, I guess. They're proud to be the largest and the most sophisticated engine component machine shop dedicated to the piston overhaul market. They specialize in crankshafts, camshafts, Magnaflux, and machining services. So, that being said, we will change our presenter here and make Shawn our presenter. And Shawn, I believe you have the controls. Take it away, sir. All right. We need to get your presentation up there. And there we go. I'm going to turn my webcam off now. And there we go. You got them full screen. It's all yours, sir.
Thank you very much. I'd like to thank Gene and Lane for their assistance with inviting me in to do this presentation today. Purpose here is to go through aircraft engine longevity and reliability so that you can kind of gain peace of mind as to where your engine's health is. Gives you some pointers to some things to look for. Also goes into a little bit more of the key factors of what is actually causing engines to be pulled in service at this point in the industry. All right, so during this presentation, what we're going to do is we're going to go through some opening thoughts. We're going to look at typical wear trends of aircraft piston engines, primarily your Lycoming and Continental engines. Types of engine wear monitoring, which includes visual inspections, visual inspection of the oil and oil trend analysis, cylinder compressions and what their usefulness is, electronic engine monitoring, and solutions for prevention, along with some conclusions and then some time for questions. I will take questions a couple times through the presentation, and then it'll be a full Q&A session at the end. All right, so engine wear, engine health, and reliability are all interrelated. Engines do wear with both use and inactivity. Right? Inactivity, or letting the airplane sit, actually accelerates wear. All sources of engine wear can be tracked, and the rate of engine wear can also be tracked using a oil sampling system. Overall engine health is the accumulated knowledge of the available wear indicators. Right. The average general aviation airplane, unfortunately, is being flown a little bit less than 100 hours per year. Given that there's over 8,700 hours in a regular year, our aircraft really aren't being used very often. So that causes problems with oil on the engine components. Since they can be corrosive, it causes pitting in steel components and causes corrosion and rust in other areas of the engine. There's leading engine oils out there for the aircraft that have claims to fame, if you will, that their oil is better because it sticks to the parts. Well, that might be true, but what happens if your oil is contaminated with acids? Another oil is going to flow at 0 degrees Fahrenheit. So how's it going to do at high temperatures, which is where you may be flying most of your summer months? So things to consider. All right, since we're all running hydrocarbon-based fuels, the combustion process actually produces approximately a gallon of water for every gallon of fuel that's burned through the engine. Now, the vast majority of that water goes right out the tailpipe with the regular exhaust. However, if you have engines with excessive blow-by, and even a normal engine with blow-by, it's normal process, you will have some level of reactants with the fuel components, and that will cause additional engine deposits, right? And combined with the lead will form into sludge and organic acids. So if you're not careful, the amount of blow-by that you're having with a cycle of short flights with long aircraft periods of inactivity will actually get you into a situation where your engine oil is acidic and is actually a promoter of corrosion within the engine. All right, so let's go through some typical wear trends. This is going to be a very quick review at this point. All right, so aircraft engines are considered complex components. In order to obtain its useful life, you must do regular periodic inspections and maintenance on the engine. All right, so when an engine is born, if you will, there's numerous things that can cause failures on the engine. The most common situation is called infant mortality, and that is a combination of potentially a manufacturing defect or human error from the standpoint of improper installation, as an example, or improper engine break-in. Right? So that infant mortality period typically runs about 200 hours on your typical general aviation engine. So things to consider if you have a brand new engine and you are in the break-in initial 200-hour phase, you are actually at a higher risk of an infant mortality type engine failure. After you get through that proverbial 200-hour window, right, there will still be normal life engine failures, and they'll be at a constant rate. So that's the flat portion of the curve on the right side of the screen. And then when it starts to ramp back up, that is the area typically where your published TBO has been derived from. So keep in mind that there's always going to be some level of failures out there, but typically once you get past that first couple hundred hours, the engines typically are fairly reliable. You just need to make sure that you're doing your inspections and keeping up with your routine maintenance. Now, if let's say you go at midlife, 1,000 hours, you do a top overhaul, that infant mortality rate starts over again. So anytime you do any heavy maintenance to the aircraft engine, you have to remember that these failure curves sometimes start over. All right, so common thought of wear areas in the engine, cylinders, right? Everyone is expecting some amount of wear within the cylinders. Normal, most cylinders are actually properly treated, have very long service lives, well in excess of half the overall bottom end of the engine life. A lot of your 4-cylinder, 6-cylinder Lycomings, the cylinders will go the entire life of the lower end also. Put that in perspective. All right, piston rings. The piston rings don't necessarily wear as much as they have a tendency to stick due to deposits, right, corrosion, and or break. Right? When you have a break in a ring, now you've got to do some little bit of surgery to go get that fixed. All right, valves and valve guides. Slow and steady wear can be expected on the valves and the valve guides. You just need to keep a good eye on the deposits that are building up on the engine and on the cylinder, and particularly in the exhaust valve area, because the deposits will be on the side with the guide valve, and if you run excessive lean potentially or excessive rich mixtures, you can actually get a deposit on the interface and accelerate your exhaust valve guide wear. Camshafts and tappets. For most of us out there, that's the most unpleasant news you're ever going to hear. If you have a camshaft which is corroded beyond limits or is worn, right, toe of the camshaft is gone, you are now into a mandatory engine overhaul type situation. You have to split the case. There's no way around it. For some engines, as you have problems with tappets, or if you have roller technology, those can be replaced on some engines in service without causing an overhaul. All right, crankshafts. Wear on the crankshaft is expected, but not nearly as much as you might anticipate. Crankshafts typically have a very long service life, easily between 10 and 14,000 hours with proper maintenance and proper operating procedures. The typical wear on a crankshaft is less than half of 1,000th on initial teardown for a typical engine. All right, so where does all this wear material go? Goes into the oil supply. Right. The rate of accumulation of wear metals is directly proportional to the expected life of the engine. So, since these engines are well known and the technology is well known, the failure modes are well known, we can actually predict when an engine will fail or start to develop major problems based off of the amount of wear metals found in the oil. Right. Many owners and operators do make the necessary commitment in time and finances to conduct oil analysis, but very few actually understand the significance of the data. So it's really important when you're doing oil analysis on your engine to do it consistently, following the instructions provided by the oil sample or the analysis company's procedures and instructions. so that you get good, consistent data. Oil analysis program is going to depend on trends. If something just breaks and it has big pieces off of it, oil trends are not going to, oil analysis and oil trending will not detect the fault. Okay, so a little bit of a pictorial here. All right, as we discussed earlier, tappet and camshaft failures in service are the most common reason for an engine overhaul. In the pictures on the right, you can see two examples of tappets. The first one is corrosion caused by blow-by. So this is a cylinder on the opposite side having blow-by past the rings in the cylinder, and that's taking a high level of dirty deposit-ridden materials, and unfortunately it blows onto the face of the tappets, and then as the camshaft rotates through onto the tappet, it grinds it in and it sets up corrosion when the aircraft sits. So that's why you got to be tracking down and making sure that you don't have excessive blow-by going through on a cylinder. That's the side effect. The picture in the lower right-hand corner, you can see a lot of little specks. Those are actually corrosion pits. And that was an engine with 196 hours in 4 years. So corrosion can set in quickly. Right? Interestingly, and unknown to many operators, many engines in service are operating with this exact condition right now. All right? The non-repairable conditions in this situation is the corrosion itself. Engines are corroding out long before they wear out at this point in general aviation. All right. Camshaft lifter or tappet interface is the most stressed system components in the aircraft engine. So this is an area that you need to be particularly careful of. In this graphic here, the first one on the left is a Continental camshaft, and it has corrosion from basically acidic oil. As you may or may not know, Continental camshafts actually sit in the bottom of the engine, so they have oil more close to them as compared to a Lycoming, which has a camshaft on top. On the right-hand side, you'll see a very unfortunate picture of a Lycoming roller cam. That is a camshaft with 300 hours in service, and it had to be pulled due to extreme corrosion pitting. Now, the true advantage with roller technology is that camshafts, the lobes and the stress levels have been greatly reduced, so the camshaft roller interface will last substantially longer in most situations. So now corrosion on the camshaft is becoming even more of an issue because from a wear aspect, the camshaft's completely fine, but because of the corrosion pitting, it has to be pulled and it's not repairable. All right, connecting rods. Connecting rod failures in service are extremely rare. Rods are simple, robust, and provide a very long service life, and they're very easily refurbished. Right? Typically non-repairable conditions, very much like what you see in the picture there, is corrosion, very low time installation. You can still see the manufacturer's ink stamps on the components. So in this case, it's corrosion. What usually also causes a non-repairable condition is going to be shipping damage, improper isolating and letting the two rods bang together in shipping. So that's kind of a problem. Sometimes they will distort due to various operational situations with the engines, and in some cases wear on the big end thrust bases to where they cannot be repaired and maintain the distance that's required between the width of the connecting rod versus the width of the journal. Crankshaft failures in service are actually very rare. Aircraft Specialties does routinely refurbish crankshafts through 4 to 5 overhaul intervals, and the typical wear is very low. The vast majority of crankshafts are not repairable due to corrosion. On the picture on the left, you can see a line of corrosion pits, and this is literally from the engine sitting idle and corrosion being able to get between the connecting rod and the thrust face of the crankshaft. So very unfortunate to lose a $10,000 crankshaft due to corrosive oil, essentially. On the right-hand side, that's a picture of a crankshaft under Magnaflux, or magnetic particle inspection. And the green lines that you're seeing that are outlined with the red, those are examples of cracks that would be found. The situation that you're seeing here would be typical of a crankshaft that was damaged from a prop strike. All right. Typically, crankshafts are condemned due to corrosion, pitting, and cracks. All right, so the types of engine we're monitoring. All right, there's options. Depends on how much information and data you're comfortable with. These get progressively better in terms of their overall monitoring for engine longevity. But they also, in most cases, get a little bit more expensive as we go down the list. So again, this is based off of the amount of data that you're comfortable with and the type of operation that you're flying. All right. The easy fix always is, whenever you can, fly the airplane, fly it with some altitude on it, with a pretty decent power setting for at least an hour, and that will keep a lot of your inactivity, corrosion-based problems within your engine at a very low rate. Okay, so on the outside of the engine, you want to be doing very well with visual inspections, looking for case condition, cylinder condition, proper baffling and cowling seals. I know that that gets routinely overlooked. If the engine's not properly getting cooling, you're going to have hot spots, and that's a good indicator of where a crack's probably going to start. In terms of the engine internals, visual inspection, very simple. Start with, when you pull the dipstick and check the oil, look at the color and look and smell the oil and see if it smells burnt. If you pull oil out and it looks nice and clean and new, it's good. If you pull the dipstick out and there's something that kind of looks like mayonnaise on the cap, dipstick cap, that means probably that your oil is not getting up to a high enough temperature to get the water out during operation. That is very typical on aircraft that are operated lean of peak at relatively high altitudes for long periods of time. The engine literally cools off and the oil doesn't stay hot enough to get rid of the moisture and the acids that can then develop into the oil. Fairly simple, straightforward. Also look at oil filters and screens, and then of course bore scoping. All right, here's a picture of a bad day. Luckily this one was found on the ground. Track down and resolve all your oil leaks. And it's an easy statement to say. Sometimes it's a little bit harder to do in the real world, right? But you need to know, and everybody knows it, right? Aircraft engines, they leak oil. Okay, enough said. But you need to know where that oil is coming from. Little wispy oil leaks are a very early predictor on the cylinders, for example, of an impending head-to-barrel separation. When the component warms up in operation, a crack will expand, and in some cases oil will weep through the crack. And then when you land and you shut down, the engine contracts as it cools, and you cannot see the crack. So just kind of a situation that you got to be careful of. In the picture here on the right, we have case cracking. The red line there is from an NDT function. And a lot of cases, case cracking is caused by through-bolt torque on the two case halves being too low. Can cause fretting and or improper cylinder installation. Can sometimes cause those. So also be careful. Sometimes an oil leak can be an indication of a start of a crankshaft crack if you're dealing with a constant speed propeller installation that uses engine oil. All right, again, proper baffling and cowl seals. Proper airflow is much better for temperature control. All right, let me stop here for a second and see if there's any questions. Lane, we got any questions on the Squawk Box?
We have one from Thomas Ralph, who is wondering, is this the same thing we were covering last week? And I was just about to tell him that this is probably review and that you'll be moving on as we go along.
Yes, there is some similarities to the previous presentation from last week. There is some new information, probably in about 10 slides, give or take.
That's it for now.
Okay.
And I noticed we also have a hand up from James. We're not opening microphones on this, so if you just type whatever your question is into the Q&A panel there, we will get to it. Thank you.
All right, so looking inside the engine. All right, one way to look inside is visual inspection of the oil itself. As in the graphic there from left to right, on the left side is your nice, clean, brand new oil. And then over time, right, as the oil's in service and it's exposed to combustion materials, the oil becomes darker in color. A good visual indication is where you see the green vertical line on the screen. When you get to that darker brown and you can't really see through it anymore, then it is time to change both the oil and the filter. All right. From a trends situation, you do have a situation where that normal color transfer, it's going to be a little bit different on every engine, but pretty much you should be in the 30 to 35 hours operating time for that to occur. If you have an engine that's typically been running at that proverbial 30-hour mark, to get that to that point, and it rapidly starts going from brand new looking oil to oil that looks like it needs to be changed in like 5 hours, for an example, then it's time to start investigating, because you most likely have a problem with blow-by. Okay. And whenever you change the oil, make sure that you put new oil and filter in regardless of the oil's time in service. Big thing with the spin-on oil filters, 50 hours doesn't necessarily mean 50 hours. In a lot of cases, the spin-on oil filters, just in normal operations, will actually start to bypass internally. They're designed to do that. And when the oil gets to a point, it will bypass automatically, and in a lot of cases that's around that same 35-hour mark. So just kind of a note to self. All right, oil suction screens. It's your first line of protection with the oil system, and it's going to capture the big pieces. All right, no necessarily trend information there other than that there's something wrong. So make sure that that is inspected whenever you can. It's recommended in oil changes by Lycoming. Continentals have a very similar setup. Unfortunately, with how the airframe installation is, it's typically very hard, if not impossible, to get to in most Continental installations. Engine oil pressure screen. This is what you're going to have in lieu of a spin-on oil filter. This is going to be your 25-hour oil change interval. What you see there in the picture is a whole bunch of what looks like nice little shiny glitter. That unfortunately is a camshaft that has come apart. So don't be afraid necessarily with a little bit of metal in a suction screen like this or in the oil filter media. The manufacturers have a fairly broad tolerance for the amount of metal that can be done or can be found and still continue in service. It's always a very uncomfortable feeling when you see that amount of metal, but it's just something where you find that type of a situation, it's time to investigate. And never throw away the data. Very hard to troubleshoot if this gets contaminated with other debris from the shop or whatever. So make sure you do a clean environment when you're cleaning these screens, and make sure that you save the data. All right, visual inspection of the oil filter medium. Very easy way to establish trends. Engine oil is typically changed at a fairly consistent interval on the airplane or on the engine. And as long as you're doing consistent oil changes and you are doing consistent data gathering with the filter media, it's a very good trend tool. Very low cost. You've already bought the oil filter. All right, so here's just some real quick examples of things that are found in, that can be found in filter media. To the untrained eye, a lot of this is going to look very much the same, but to the trained eye and with the use of metallurgical labs, it is actually fairly easy to determine where the materials are coming from within the engine. Very quickly, on the left is tappet material. Right? That's a spalled lifter. That's a lifter that's coming apart within the engine, and that's a way to identify it early on. On the right looks like a whole bunch of dirt. It's actually phosphate-laden iron from a set of Continental cylinders, and because of how they were heat treated and coated, it was a very easy indicator to determine where the source of the material was coming from. On the left, on this slide, is the bronze bushing material. That is an oil pump gear, and that, even though it looks horribly big in the picture, it's actually quite small. All of these pictures are taken under magnification. This is something that's actually correctable without an engine overhaul. Oil pumps are accessible on these engines. On the right, brass slivers. Sometimes you'll also see like a steel whisker type setup, and those are indicators that come from a going or a recently replaced starter adapter. The starter adapter failed. The engine oil will have taken some of these whiskers through, and you'll probably see it in the filter for another oil change after the starter adapter change. All right, on the left is a whole bunch of aluminum from a piston pin plug. They do wear on occasion. Again, if it's caught early, you can catch that and do the necessary cylinder repair without causing a fotted out engine, which would dictate an overhaul. On the right-hand side, a whole bunch of what looks to be trash, because it is. This is what it will look like after an engine overhaul. On the first engine run, when you cut the filter open, there will always be some level of debris, FOD, foreign object debris, in the engine. Cleanliness is extremely important when maintaining these engines and having them opened up. But this is a typical example. Some of the stuff there is Scotch-Brite, cleaning pad material, some silicone sealant type material, a couple corners from gaskets that from assembly, when it ran, they flaked off. So that's fairly typical. All right. On the left is a bearing material. All right. To the untrained eye, what's on the right-hand side looks fairly similar, but that is actually copper bronze from a vermotherm, and that is related to the oil control system for temperature, and that is easily replaced without any major invasive engine work. All right. Piston skirt fracture on the left side. On the right side, it's rubber, and that's going to be if you have a engine that has a gear-driven alternator. There's an elastomer on there used for vibration dampening, and when that comes apart, you will sometimes see it in your oil filter media. All right. Some more pictures there of bearing material. All right. All right, let's look at bore scopes. All right, so another visual inspection mean is going to be bore scoping the inside of the engine, or the cylinders in particular. Bore scopes are more readily available than they ever have been, so they work out very well. Easy to operate. If you have one of these or considering getting one, they're well worth it. The couple of cautionary points with getting a bore scope and bore scoping your cylinder for the first time is it's going to look scary to you. So get with some folks that have done this before, and the key is to go in and start getting trend data. Obviously, you can find a crack early on, but the big picture with bore scope is to understand what the baseline looks like and then take subsequent bore scopes and take pictures of the items in the cylinders for comparison and see what you're looking at in terms of color changes, erosion, corrosion, etc. Excuse me. All right, so here's some wonderful pictures. All right, so bore scopes, just like oil changes, need to be done at regular intervals. All right. It's really important to get some experience with looking at the bore scope and looking at the particular engine to know what normal is going to look like for that engine. And that's why it's important to look whenever the engine is already open, let's say for a spark plug service. Don't necessarily have to go in specifically for the bore scope. Just line it with a regular scheduled maintenance that you already are gaining access to that cylinder. On the upper right side, you can see a crack emanating to the spark plug hole. So that's why you can see some of the advantages of the bore scope, because that crack, it would not be visible on the exterior of the cylinder at this point. All right, lower picture is the sidewall of a cylinder, and that is corrosion all over the place, along with deposits. Not a good day. All right. Always compare whatever video or pictures you've taken so that you can see what the level of deterioration is and what its progression rate is. All right. So burnt exhaust valves have long been a leading cause of cylinder failures and power loss in piston engines. right? Valves that fail to seat properly are subject to severe and uneven heating, right? And based off of color indications, can be determined that they are in imminent failure mode. All right, these three exhaust valves here, are excellent examples of perfectly good exhaust valves. What you're looking for when you're looking at exhaust valves is going to be the nice symmetrical round pattern, right? And the dark to orange color is perfectly fine. The saying goes that burnt pizzas are okay. If you see the picture on the far right, that's an example of a properly patterned exhaust valve. The additional deposits that are on it are due to running the engine richer than it needs to be, or that cylinder is running richer than it needs to be. So that's kind of what is the extreme case. What you're really looking for is pretty much in the middle. That's typically what you're going to see. All right, so what to look for with the exhaust valve with a bore scope is going to be you want that symmetrical pattern. In this scenario here, as you can see, the picture is going from 1 to 2 to 3, that the circular color pattern is not symmetrical, right? It's uneven. And as that goes along, if you look at the 12 o'clock position on the valve, you can see that it's progressively getting more of a burn pattern, and it's not symmetrical. So you got this little arc going on here. In the third picture, you're seeing that the burn pattern is continuing to migrate inward and starting to get ugly. Okay, so in the fourth picture, whenever you see green on the valve, it is time to stop, and it is time to make the necessary repairs to the exhaust valve and or the cylinder. Okay, once you get into green, you're within 50 hours of the exhaust valve cracking / failing, and you definitely don't want an exhaust valve to fail. That can put you into a seriously bad day. So this is one of the indicators to look for with a bore scope. All right, so there's many trends that can be established with both external and internal indicators. Right? The key with this, just like everything else, is consistency. So make sure that you get consistent data. You're looking at your oil changes consistently. You're looking at bore scopes consistently. Oil trend analysis needs to be done consistently with those oil changes so that you get a good overall picture. Right. Save the data, take pictures, right? Bag and tag the stuff, put it on the shelf, right? Because nobody remembers what it looked like 6 months ago. Trust me. All right, monitor oil for sudden changes in color or smell. That is a very easy, inexpensive way to get an indicator of cylinder health. All right, so a little bit of new stuff for Thomas. All right, so oil selection. All right, so what to do is picking out the proper oil, because what we're really finding out in the industry is, with the amount of corrosion and the lack of use of most general aviation aircraft, with it sitting on the ground, we've got to be much more aggressive with arresting the amount of corrosion that's happening inside these engines. So your basic oil, like your Aeroshell W100, right? It's a good oil, right? They're all good oils. Base stock, it's got dispersants in it, antioxidants and anti-foaming, right? Works good, lasts a long time. But it doesn't necessarily have the amount of corrosion inhibitors that you may need based off of how much you're flying or the environment that your airplane lives in when it's not flying. If you're a fan of multi-weight oil, example is the Phillips 20W50, right? And that is just a straight 50 weight oil with a viscosity modifier, to obtain the 20W rating. All right, some of your more premium oils, like the Aeroshell 1550, the Exxon Elite 20W50, all right, they have an anti-wear and they do have a little bit of a corrosion inhibitor, but in most cases, the use of the additives within those oils can actually cause other problems with seals. So something that you got to watch out for. Okay, so picture on the right-hand side is the common Cirrus small sump Continental engine, and in that picture it was run with your standard oil, no additional additives, regular operation, 800 hours, and you can see that the level of deposits and heating that that engine incurred. That is not a special case type picture. That is normal operations for that type of engine. All right, so what you're seeing here is deposits on a piston. All right, this is your typical, what you'll see in service, just with normal operations, normal oil, that's it. You're going to have situations where you're going to have a lot more deposits. Notice that this ring is actually stuck, right? It won't be able to rotate in service like it's supposed to. You've got corrosion on the ring itself, and you've got sludge buildup, and then because these are not being able to function properly, now you've got additional scuffing on the piston. So this is not what you really want to see when you have to take an engine down or take a cylinder off. All right, because of the corrosion situations going on within the engine, and particularly within the cylinders, because this is an easy way to get some pictures. On the right-hand side is a Continental IO 550 with 720 hours on it. It suffered from stuck rings, rust on the cylinder walls themselves, and it got a polished pattern, so it lost its honing marks. On the left-hand side would be what the new steel cylinder bore would look like, same cylinder. So you're seeing what it should look like new versus what 720 hours looks like. That is an extreme case of the amount of wear. There should be a lot more of the cylinder honing marks that should be visible. You can basically see probably about 5% of them in that picture. Just kind of put it in perspective. All right, so here's some pictures that we're able to obtain during the CamGuard certification process. These are the actual photos that were taken to provide substantiation to the FAA. All right, so these pictures, this was a aerobatic aircraft that was flown during airshow routines. It's an IO 540 with 300 horsepower, 531.5 hours through the testing program. These are undoctored. These are just the straight data pictures that were taken. The oil on the parts was 54 hours in service after it had sat after the airshow season for 3 months. All right. So the engine from the engine monitor showed routine oil temperatures at 300 degrees Fahrenheit and cylinder head temperatures in excess of 450. All right, so on the left is an engine that has had the CamGuard in it, properly dosed per the instructions for the 530 hours. Picture on the right is the piston from the control, which ran standard W100. Right. Picture on the left is a piston from the engine, or from one of the cylinders. All right, there's absolutely no deposits, and all of the rings are completely clean and correct. The deposits that you do see on the very upper side of the piston are normal from the combustion process. Okay. All right, if you remember back to the picture of the Cirrus small sump Continental, and what the level of deposits and varnishing that occurred on the parts. Compared to this picture, you can see that there is essentially no deposits. Wherever the oil and oil additive combination can reach in service, there is no corrosion. Right. Here's a picture of an exhaust valve guide, and when measured, it still met new specification with 500 hours. Okay, accessory box, accessory case picture. You can see what the level of deposits are, and notice how the oil is still clinging or attaching itself to the metal after disassembly. Pistons, pins, pushed out with your finger. That's not typical of a 500-hour engine. These are the lifters that came out of the engine. Notice that there's a uniform circular pattern all the way around, and as part of the test, the aircraft sat stagnant for about 4 months from the end of air show season before the engine was pulled for evaluation. All right, camshaft lobe. This is a Lycoming. Keep in mind it had an inverted oil system on it, so at every engine start it had no effective oil pressure for the first 20 seconds, and during the air show routines, routinely flew for a cumulative time of 1.5 minutes with 0 oil pressure to the cam. What you see in the picture is slightly polished, which is considered normal in service and is by no means abnormal. All right, here's a piston that came out of a TSIO 520 at 835 hours, and you can see that, again, proper use of oil changes and corrosion inhibitors will definitely protect the engine. All right, so let's take a look at what's in the oil real quick. Actually, do we have any questions out there, Lane?
We have one that kind of goes back a little bit. One person wanted to know, would you please describe exactly what you mean by blow-by?
Okay. Blow-by is when the engine is on the power stroke and the spark plug fires and it ignites the fuel-air mixture within the cylinder. All right. Of course, the expansion of the gases is going to push that piston down on the power stroke. There's a set of rings on the piston that provide the seal between the piston and the wall of the cylinder. If for some reason those set of rings cannot make good contact because they're corroded or they're stuck or they've broken for whatever reason, then you're going to have high pressure combustion gases blow by that seal or those rings, and that's going to blow into the crankcase of the engine. And typically, because it's horizontally opposed, those deposits in combustion gases disperse through the case and directly onto the opposite side tappet in cam lobe areas.
So it's not gas escaping past the exhaust valve, it's the rings.
It's the rings, that's correct.
Okay. Another question is there any way to know if your oil filter is operating in bypass?
No.
Okay. And any negatives to using CamGuard?
No negatives to using CamGuard. Do we have any specifics on what they're operating or anything like that?
No, that was all they just asked if there was negatives to using CamGuard. And I have a personal question. So is there an additive that you would recommend to add if you're like running, say, Aeroshell 100 that would help with making the oil better against corrosion and stuff, or just make it last longer?
CamGuard is definitely the product to use out in the market.
Okay.
I've used it in my own aircraft for, I'm getting old, 14 or 15 years at this point. And I have not had any problems with the engine. I am 14 years since major overhaul, and it had CamGuard in it since since break-in. You don't run CamGuard until the engine or the cylinder is broken in. Right. But yeah, it's a good product. They know what they're doing with it. It's been tested. Went through a complete FAA observed testing program to show that it would do no harm, and meets all the necessary requirements.
Okay. And is that something you add at each oil change, or is that something you would add along whenever you're adding oil?
Yes and yes. What you want to do is follow their instructions for dosing with the CamGuard, and it essentially boils down to you maintain a 5% mixture of CamGuard in the oil system. So it's pretty simple. A bottle of CamGuard treats 10 quarts of oil, if I remember correctly.
Great.
Yep.
Thanks.
Okay. Yep. And when you do replenish oil, right, you put a quart in between oil changes, for example. You also want to put that proverbial, what would that be, 1.6 ounces per quart of CamGuard to keep the mixture or the concentration correct.
Right. Thanks.
Cool. All right. Let's continue on here. Okay, so oil analysis involves the sampling and analyzing of the various wear materials because based off of how much wear materials is in the oil, we can determine what the useful life of the engine remaining is in most cases. This is not new magical science. It was first developed in the 1940s when diesel locomotives came out. Militaries and airlines rapidly adopted the technology with turbine engines. If you came from military aviation circles, you know it as soap samples. It is a analysis that will definitely predict specific issues within the engine. There's normal wear values that are known, and then if you start getting out of that normal range, then it's time to start investigating, and knowing what metal it is tells you where to go in the engine in most cases. Oil analysis is recommended by both Lycoming and Continental Motors. In Lycoming, it's service letter L171, and Continental Motors is Consolidated Standard Practice Manual is now where that information is located. Excuse me. All right, so spectrographic oil analysis identifies concentration in parts per million of the wear material in the oil sample collected during an oil change. Quick tip, when you do your oil change, make sure the oil is warm. As you drain the oil out, let about the first quart drain by, and then put the little sample cup into the screen to collect a clean oil sample so that it's not contaminated by any junk that might have been around the drain valve or on a hose or something that you're using as you started to drain the oil. All right, so analysis is going to begin with the first oil change sample. first sample establishes a baseline, and then your subsequent samples taken over time will establish the trend. Again, just like bore scoping, consistency is the key because you want to make sure that the oil has about the same amount of run time on it so that you can get an apples-to-apples comparison. All right, so what's all the stuff that's going to come in on that oil analysis report? Well, all that, depending on what you've got. So very quickly, we'll go through that. So what's in the oil? Aluminum. Most of the engine's actually made out of aluminum. Typical area of aluminum in the oil is going to be from piston skirts, piston pin plugs, or a fretting crankcase half. Through bolt torque on cases, is extremely important. It's important that they be properly inspected and checked at regular intervals, and it is imperative that proper procedures are followed during cylinder changes to maintain that torque value on the case halves and to keep the torque value on your bearings on your crankshaft. Chromium, all right, chrome, if you will, chrome-plated pistons, piston rings, cylinder barrels if they're chrome-plated, and exhaust valves. So if you've got regular steel cylinders, you're looking at an exhaust valve. All right, iron, principal wear element, all right, it's going to come from steel cylinders, lifter faces, cam lobes, gears, crankshaft, and camshaft journals. Depending on what it is in the levels in oil analysis can lead you to a finding in a filter, and based on what you find in the filter can probably be analyzed to determine which one of these items it's coming from. All right, copper, bronze bearing shells, and don't worry too much. Sometimes you get lucky and it's only a deteriorating oil cooler, but if you see a spiking amount of copper, you want to make sure that you check that oil cooler, because an oil cooler failure in flight pretty much equals an engine failure in a few minutes. So something to keep in mind there. Also, I've run into this a couple times now, and it's been confirmed at the manufacturing level. If an operator changes to Aeroshell 15W50, the additive package in that oil will work on the copper flashing that's on the camshaft, and that copper flashing is there as part of the manufacturing process for the hardening of the cam lobes. It has nothing to do with the strength of the material. It's sacrificial in nature, but it will, if you just changed over to 15W50, it may show up as a spike in copper, so just kind of an FYI on that. All right, lead. Lead's going to come primarily from aviation fuel. If you're not running 100 low lead, well, it's coming from bearings. That's all I can say about that. The picture there is actually the front nose of a fixed pitch propeller Lycoming, and the stuff that looks like putty in there is actually lead in deposits from fuel. And keep in mind that that is completely inside from the oil system. That's how it gets up there. The oil gets trapped up in there and leaves the deposit. All right, tin. Tin is the outer layer, tin flashing on some bearings, depending on which engine and what model you've got. Sometimes bronze parts are going to have a tin component to it. All right, nickel. Typical sources of nickel, again, are going to be your exhaust valve guides. And if you've got nickel-based cylinder coatings, that's going to show up there. Potassium, that's going to be coolant-based if you've got a liquid-cooled engine. Manganese, Typical source of that's going to be greases. Silver, very rare. If you're running a radial engine, you might find silver on your report, or if you've got a really, like a classic Continental E185, the bearings that were in that had silver flashing on them. All right, boron, a corrosion inhibitor found in coolant. Silicon is basically dirt. If you get a high count of silicon on your oil analysis, it's time to go look around your your air filter and make sure that that intake box is nice and sealed up. If that's not the situation, maybe an additional dab of DC4 got put on the oil filter gasket if you use that type of setup, and that can set it up for extra silicon. If you had pretty much fresh out of overhaul type situation or heavy maintenance, there may be some glass beads from bead blasting operations, cleaning operations on an engine component, and maybe not all the beads got out of an oil passage or something along those lines, so it may elevate your silicon level. All right, phosphorus. Phosphorus you may find on a report based off of what oil you're running, because phosphorus is used as one of the anti-wear protections. You're going to find that if you're running Exxon Elite 20W50, Aeroshell 1550, or any of the plus versions of the Aeroshell products. All right, and then items that are typically found in an automotive oil. So if you find any of these in your aircraft engine, it's sometimes a indicator that you need to watch your oil, what's getting put in. All right, conclusions. Proper selection of oil and oil additives, all right, based on the aircraft operating conditions is going to be essential. Whenever you can, do what you can to make sure that you're reducing deposits. If you're reducing deposit buildup in the engine, you're inherently decreasing the amount of corrosion. And if you're decreasing the corrosion, you are definitely increasing the overall service life of the engine. Unfortunately, in general aviation, we're losing more engines due to corrosion than wearing them out due to operation. When you can, fly your airplane. Right. Oil analysis is definitely the best trend indicator for engine health. Right. Also aids in troubleshooting of faulty components. Don't be alarmed necessarily when you get an oil analysis report and it has a high level of a material. That material may be coming from a component that is external to the engine or is easily accessible, which does not require disassembly of the bottom end or an overhaul. Many cases, simple fixes to an individual cylinder or to like the vermitherm can arrest the problem. Just remember that all wear metals are going to end up in the oil. Right. The rate of engine wear determines the useful life of the engine. All right. Make sure you're conducting oil analysis at consistent intervals. You need to have at least 10 hours on the oil to get good data through the oil analysis. And you need to make sure that you record and replenish the oil mounts and the times. That helps with the lab so that they can get a good calibration number for the wear mounts. Also, very important to make sure that you select one lab to conduct all the oil analysis. You can't really mix and match reports from different labs. It's really important to make sure that you have a consistent set of oil analysis reports from the same lab so that you're have that true apples to apples comparison. All right, cylinder compressions. Go through this. Differential pressure checks are sometimes known by some folks as a leak down test, is one of the quickest and easiest ways to determine top end health of a piston engine. You got to be cautious with this. It's just a snapshot in time. So just kind of be careful with it. There is going to be theoretically some trend information in the logbook, but you need to be really careful with how you use it. It's really important that you're looking for consistency with cylinder compressions as opposed to an arbitrary number like 64 or 80. You really are looking for all the cylinders within 5 psi of each other, and that if you have more than a 10 psi split between any of the cylinders, all right, you need to investigate and find out what's going on with it. It may be something as simple as you've got a little bit of deposit or debris sitting somewhere that's preventing the valve from fully closing, or you've got just a little bit of stuff going with a ring and just needs to run again, and it'll clear itself out. All right, so air leaking past the rings is not an immediate cause for concern. All right, rings do accumulate deposits in normal operation. If you're using an oil additive, it's definitely going to greatly reduce the deposits, because the relative motion of the rings while the engine is running will actually knock off any deposits that start to build up, and it keeps itself cleaned out. Air leaking past a valve is cause to investigate. Don't wait for a trend, right? If you can detect that there's air leaking past a valve, either intake or exhaust, doesn't matter. You want to investigate that, get the borescope in there. If you've got an electronic engine monitor, you want to be looking at that data. You know, don't panic initially. You just got to go in and get some more data. More times than not, it's just a simple piece of FOD, a little piece of debris preventing the valve from fully seating. Right. We're seeing a lot of cases, for those of you who are a little bit more maintenance side oriented on this, big bore Continentals running lean a peak. Keep an eye out. Sometimes the deposits are now showing up on the intake valves. All right. Again, make sure you're keeping the data. All right, so again, differential compression checks, they can be used to establish trends, but you got to be a little bit careful with them. Just remember, it's a snapshot in time, right? Consistency between the cylinders is much more relevant than just an arbitrary number. All right. Lycoming and Continental have different philosophies when it comes to differential pressures. Compression checks. We're really finding as time goes on that it's a snapshot picture. It's not truly an overall trend piece of information. So just kind of look for that consistency. That's really the key with compressions. Right? It is okay to consider cylinders as a line replaceable unit. Don't think that you've got to do a complete top if you've got a problem with one cylinder, right? One poor performing cylinder, you know, don't throw the baby out with the bathwater type situation. Do proper troubleshooting, determine which cylinder it is, right? And then if you do need to change out that cylinder, right, do them one at a time. If you're doing multiple cylinder changes, be very careful to maintain the proper torques on the through bolts and cylinders. All right, engine monitors. All right, most all electronic monitors record the data and is accessible, excuse me, for trend analysis. It's very nice to have, but they're getting less expensive, relatively speaking. And a lot of airplanes still don't have them, but if you can get into a situation with an electronic engine monitor, it's a very good trend tool. You combine that with oil analysis and the ability to pull up the data. It's a very effective means of determining the long-term health of your engine, and it's a very good way to determine in flight if you've got an immediate problem. There is third-party software available, and there are also professional analytic services available to keep track of your engine's health. It's all a matter of what you're comfortable with. Do you want to get the data and process it? How much data are you comfortable with? And do you want a second pair of eyes to be checking over the engine health? It's all a matter of what level of data and analysis you are comfortable with. Here's just a generic screenshot of what a engine monitor would look like in terms of its reporting data. To some of us, it looks like sonar off the Marianas Trench. To the rest of some of us engine geeks out there, it's very good troubleshooting information to see how well individual cylinders are doing, how the engine and airplane are being operated overall. You can even overlay this information with ADS-B information now. So watch out there, pilots. All right. Electronic engine analyzers. All right, just kind of remember that the phrase that we use is it's another tool in the toolbox. It's another tool that you've got in the panel. The other thing is me be pilot also. Remember to keep flying the airplane and don't look at all the bells and whistles sometimes. All right. Overall, engine monitors used in conjunction with oil analysis, bore scope, visual inspections can give you a very clear picture of engine health, and combined can give you a very good and accurate indicator of the useful life of the engine. All right. So how do we know our engine's healthy? All right, or what the engine longevity is going to be? The trends are a good predictor of overall engine health. Right, multiple set of data sources available to establish the trends. Right, the level of confidence in determining the engine's health is directly proportional to the amount of effort you want to put into it. Consistency of the data is key. You can't do just one piece of it and do an oil analysis like once a year or every other oil change and really expect to get your money's worth out of it. So just remember that engine reliability is simply being aware and acting on on emerging trends, right, or sudden changes in any particular parameter. Okay. Oil consumption, right, the amount of oil that it's using or not using can sometimes be an issue, right? Remember, the engine's going to be airworthy as long as it makes full rated power, right? The duration that it takes for the oil to turn black, right? That's an indicator of an impending problem. New or worsening oil leaks is definitely something that you want to get on top of. I've seen multiple situations now where cylinders were cracked through more than 3/4 of the circumference of the cylinder, and it wasn't detectable early on because of where the cracks originated, and they only leaked oil when it ran. And when it shut down, there was no way to find it, right? So we figured it out over a long period of time, but it's a sickening feeling to find a crack that's 6 or 7 inches long in a cylinder. So you want to find them early. Excuse me. Make sure that if you can, electronic data is good, but data can sometimes be overwhelming. You combine an electronic data analysis with an oil analysis program and you're in pretty good shape. All right. So conclusions, all right, trending can be a simple collection of the stuff that you're already doing with oil changes. That's an easy way to start. Remember that corrosion is getting these engines far earlier than they should be. Right? They're just not wearing out anymore. Corrosion is taking out very expensive components within the engine. So the easy thing to do initially to arrest that is proper maintenance, proper oil changes, using the additives appropriately so that you get maximum protection. Right? Get the most out of that oil, right? And out of your oil additive. It really does save you a lot of time and money down the road. It really does. All right. Trend with borescope and taking photos. Right. I can't stress enough that you need to take photos because you cannot rely on, oh, I'll remember that. You won't. Trend with an oil analysis program, and if you can, spring for the electronic engine monitor. All right. The more you know, the more informed you are, the better off you're going to be, and the more prepared you're going to be to fly that airplane. All right. Quick thing, quick shout out, some recognition and thanks. Aircraft Specialties, CamGuard, Divco, that overhauls crank cases in Tulsa, Oklahoma, and Pinnacle Aircraft Engines in Alabama, all contributed data and their expertise in this presentation. And I'd like to thank them for the opportunity to present for them. All right. And I'll open it up for any questions.
Shawn, we have mostly CamGuard questions. Can you, does Continental recommend CamGuard for their IO360? And can it be added to AirShell W100? Just for a couple.
All right, so let me tackle the, can it be added to AirShell W100? Yes, it can. CamGuard can be added to any approved aircraft engine oil. Okay. It was tested to make sure that it is compatible and will not interfere with any of the oil's functions or operating parameters. For the question concerning Continental motors, with the IO360, Continental has not said yes or no directly. Continental entered into an agreement about 6 years ago where CamGuard was actually being furnished with new engine overhauls. So you can kind of take that with as an endorsement or not an endorsement. Yeah. But there is no technical reason not to use CamGuard in that engine.
Is there are there any problems with using CamGuard in a mid-time engine?
No, there are no problems with that. Just like anything else, you know, it's an additive. It is not a miracle in a can. Mid-time engine, you know, 1,400 hours, it's absolutely no problem. It'll actually help if you've got deposits, particularly on the rings, because of the relative motion of the rings, the deposits will pulverize, and in most cases, the rings will actually start turning again.
Cool. And can you start using CamGuard after, say, 10 hours on the oil, or does that need to go with the initial oil change?
Okay, are we talking fresh out of overhaul, we think?
It sounds like the question is, if you didn't put CamGuard in when you changed your oil and you're 10 hours on your way to your next oil change, can you add it in kind of after the fact and begin using CamGuard at any point?
Yes, you can start using CamGuard at any point after the engine has been broken. I would not use CamGuard until you are very confident that the cylinder, the rings have broken into the cylinder, so that you've got that good mechanical interface that you need. But adding CamGuard, a couple hours or 10 hours or half-life of the oil is absolutely not a problem.
Right. So it wouldn't be something you'd want to do. You definitely would not want to do it during engine break-in, but otherwise you can start using it at any point.
Correct.
Yeah. And last question, do you work for CamGuard?
No, I do not.
Oh, and is CamGuard okay with a turbo?
There is no reason why it cannot be used. The one piece that I would tell you from my knowledge of CamGuard is it was not part of the FAA observed testing, but I know that the company extensively tested it on turbos.
Cool. That appears to be all the questions we have.
All right. Well, I'll jump in. We're just about out of time here. I want to thank both Shawn and Lane for giving up their time this afternoon. Shawn shared with me before we began that he's been up for about 30 hours, so he did good to stay awake for all this. Good job. We will move on here to wrap it up. In case you didn't know, Avemco offers a safety rewards program. Attendees at this event or any of the other events, or anybody who takes safety-based educational courses, can receive a percentage off their annual Avemco premium at the time of the quote. You just have to let them know. And they told me that that also counts if you watch the video of any of the webinars that we have done in this series. They take your word for it, so just go for that. This slide is outdated, need to move on. It says one more left, and there isn't. This was the last of our series of the Avemco Pilot Talk series webinars. We're going to take a little bit of time off, but Avemco has renewed us to resume again in October. So I'll be looking for that. And also something exciting and new. If you check out my newsletter, Vectors for Safety, you can sign up for that if you haven't already done so on the Vectors for Safety website. I'm going to announce something new and exciting coming up that just came up today. Nobody knows about it yet. So please check that out if you're not there. So we thank all of you folks for attending and spending some time with us this afternoon. Special thanks to Shawn and to Lane for giving up their time today to do this, and we appreciate everybody's attention at this. And please always remember, fly like your life depends on it.